Next up, I'm happy to introduce Dr. Adam Rysanek. Adam will be speaking to us about architecture and cooling. He's an assistant professor of environmental systems at the UBC School of Architecture and Landscape Architecture, otherwise known as SALA, I'm guessing. There we go. He's an expert in green building design, construction, and operation with over 10 years of experience engaging with high-performance building projects in Canada, Europe, and Asia. Dr. Rysanek holds a PhD in engineering from the University of Cambridge and a Bachelor of Applied Science and a Master of Science Engineering from Queen's University. So please join me welcoming Adam. Thank you.
Thank you. I'm going to orientate myself around what I think are the different clickers, right? So this guy, that's my, is that my laser? No, which one's my, oh, all right, well, I'll start there. I'll see if I need a laser in a second. This is already foreshadowing the bit. So I'm a mechanical engineer that is a faculty in a school of design. It's conducive to a form of academic personality disorder that I'll try to navigate for the next little while. And this image already, I think, unfortunately, answers a pop quiz I was going to ask everyone. And try not to think about this image when I ask you this question. And I'm not going to ask you to close your eyes because it's kind of weird, but I want you to just think for a second about your ideal workplace, where it might be in the world. And is it a room? Does it have four walls? It might not be a room. Does it have a desk? Are you working on a desk or a sofa? Is there a window? Is there a view somewhere? Are there plants? I'm going to get back to why I'm asking this in a little bit, but I have a suspicion that for many of us, it might not look much different to this graphic. But I want to get there in a different way. First, climate. I mean, we've heard about that, and actually we've seen this image. I'm not going to say anything more about that, but I do like this statistic of what happened. If you weren't really that familiar with what happened in Lytton and the temperature recorded, it was about 4 degrees just shy of the hottest temperature ever recorded on the planet last year, and that happening here in glorious Canada for all the non-Canadians who would say how cold it is in our country. I'm an occupant in this building. It's CIRS, Center for Interactive Research on Sustainability, and for those of you who are in the province and the city, you might know the legacy of this building is being one of sort of a hallmark high-performance building, naturally ventilated building, very sustainable building to demonstrate high-performance building design on the West Coast. A few years ago, we took historical data from this building. We have a lot of the sensors of indoor air temperature and other conditions inside the building. We have also weather data, and applied different form of machine learning techniques and compared that to thermal comfort models to make a prediction under the RCP 8.5 climate scenario, which we know we're heading towards. To what extent will the indoor spaces, the offices in this building, comply with thermal comfort models in the near future? And we're seeing already that by, well, now, and definitely in the next 10 years, already this space will, and I would point to that, exceed the city of Vancouver's and really most of our kind of Canadian presiding thermal comfort codes on comfort. At least 20 days, 10 to 20 days, in about a decade from now, out of every summer, you would expect the temperature inside the space for at least 1 hour of those days to exceed thermal comfort constraints. Now, that can be 26, or that could also just be hot. Some days it's going to be 29 and people feel uncomfortable. Other days, 27. It's a mix of it, how it plays out. But it's going to happen at least 1 hour every day for about 20 days. And you have to think about employees in an office space and the managers, and how long will a manager tolerate employees complaining that it's too hot in an office until they say, we're going to get air conditioning. And this is being faced by a building that was designed to withstand our climate from a natural ventilation standpoint, and very likely for a vast, large number of our buildings, as we know, residents here in this town would say, we're already probably there in terms of requiring cooling of some sort. Now, we did a different set of studies during the pandemic, and it relates to radiant cooling, which I'm going to talk about, and you heard a question I asked, and also related to COVID. There's a lot in the last few years we've spent time focusing on how to increase fresh air rates in buildings, particularly through HVAC systems. We did a study that tried to model what would be the implications of taking a standard central HVAC system, like kind of an all-air system where we count on air for all heating, cooling, ventilation, and increase the outdoor air rates. And surprise, surprise, that increases the energy demand for a mechanical system quite a bit. We then looked at it at the very far right here. What if you had a radiant cooling system that's coupled with natural ventilation, where you rely on the windows being open and you take the edge off of the heat with radiant systems, not with air-based systems? And it saves more energy than it actually increases in the settings where natural ventilation can actually provide sufficient air changes indoors. We had the data for this because several years before, I also did a postdoc in Singapore and was still doing a project there when I got to UBC. We had an idea for developing a radiant cooling panel that would not condense in a really hot, humid setting. We used a very, very fancy material known as a plastic garbage bag to enclose this cold panel. Low-density polyethylene is transparent to infrared, but air doesn't go through it. And we had a demonstration facilities like this in Singapore where it was outdoors, it was 31 degrees Celsius and high humidity, and we had test subjects enter this pavilion that was cooled to a radiant temperature well below the ambient dew point temperature. And after a period of time, we had people in 31 degrees Celsius and high humidity saying they felt comfortable or cool. That's why I had a question, and we know that radiant systems, and it all works in the balance, there are different ways in which we can affect the heat balance on the skin, and radiant systems are one of them. And we did a version of this in an indoor setting as well. And this was in Singapore before too, and I could talk more about it, but long story short, say with maybe radiant systems, if we had more radiant heating and cooling systems. With radiant systems, you don't need very cold water, you need milder temperature water. The heat pumps used to generate that chilled water are much more efficient than the heat pumps to generate chilled water for HVAC systems. And if I wanted to talk for 30 minutes about radiant cooling, I could do so. I won't. I will foreshadow maybe one more thing, see if we want to really talk about the neat stuff about radiant and how we might address heating. Some of this stuff that's emerging is pretty interesting. Work in Purdue in developing selective surfaces. They're about to release a commercial paint that is so reflective in the shortwave band where solar energy is received and so emissive in the long-wave radiation band where we emit and our building surfaces emit radiation that in full sun, the surface temperature of the paint is cooler than the ambient temperature. Their commercial version of the paint is about 1 or 2 degrees cooler than the ambient. Imagine a building that in full sun, full heat is emitting radiation to the sky, then absorbing solar radiation. Pretty neat stuff in the pipeline. But I'm somewhat frustrated by this pipeline of technology because the part of me that's the architect or the faculty in architecture looks at all of this stuff as saying, we've been here before, we've done this before, none of this is rocket science. We've actually known how to do this for a long time, and we're constantly in a loop of trying to convince building developers and designers and occupants to try to initiate and install these ideas that, in fact, we've known for quite a long time. We know, say, and I don't know how many of you thought about plants and windows, we know that as much as it's maybe observable, it's also psychological and cultural than many of us. In fact, some could argue that it's human, that we want to be in spaces that are far more natural and connect us with natural settings. Probably the majority of us don't mind having plants, as opposed to the majority of us saying, I want no plants in my space whatsoever. Probably many of us would say, I want a window, as opposed to saying, I don't want a window. And I bet some would even say, hopefully many, I wouldn't mind if that window is actually openable. Switch gears to COVID. I don't know if anybody remembers this graph. Right at the beginning of the pandemic, I remember this one. That got a lot on the top left. There's some of the early studies of transmission. This was a call center in Korea. Every red chair was actually a COVID-positive case, and they were looking at ventilation and showing how physical distancing and separation between different wings might have a play. And that was very early on, and something else happened early on in the pandemic. ASHRAE created an epidemic task force to evaluate the scope of this problem, a respiratory disease that needs rapid interventions and recommendations and guidances for tenants, for developers, for cities, for policymakers on how to protect us from a transmissible disease. Here's a pop quiz. I hope I'm not moving this next. How many of you might live in a condo or an apartment building in Canada that would have been built since the 1990s? If not you, maybe your kids might live there. Apartment building? Some are. I know if we're coming to a lot of houses. I'm sure for those of you who live in a multifamily building that has maybe mechanical ventilation, would you think it's a good idea to open the windows from a recommendation standpoint or keep the windows closed as much as possible during the pandemic? Shout it out if you think the recommendations were saying balance it or keep the windows closed as much as possible. ASHRAE's guidance released in June 2020 for multifamily buildings on row 2 said if the building is equipped with a ventilation system, and pretty much all condos since the 1990s would have a ventilation system, ask residents to open windows as little as possible, particularly windows within 10 feet of a neighboring window or an outdoor location where people gather. I wonder if that's telling you you should open the windows and get ventilation, or sending you incentives to not really open the windows as much. The FAQ that still exists for ASHRAE for residential homeowners, and this is also for single-family homeowners, there's a question there at the top left: should I open my window to provide more outdoor air and reduce the risk of COVID propagation? The first words are not necessarily. And then there's an entire set of paragraphs that give the caveats of why you don't want to open your windows due to thermal comfort issues. The science would say none of this is wrong. I'm not articulating that it is wrong and there's somehow something being misleading here. But I would point you to our European colleagues across the pond in climates not dissimilar to ours, and in their recommendations, they left it pretty simple: open windows regularly, even in mechanically ventilated buildings. How are these two things so different? How is it that we've come up with recommendations here to generally not rely on these? We don't even talk about it. Natural ventilation doesn't really come up in our lexicon. It's that architect's issue. This is where I will get more into anecdotes and histories, but we look a lot at the history of air conditioning in North America that did a lot of good in many ways technologically. Willis Carrier inventing air conditioning. First air conditioning system in an office building was in the same city that air conditioning was invented, in Buffalo, New York. Frank Lloyd Wright designed the first air-conditioned office building that had these massive ducted columns. The ductwork going up and down was like the actual 4-point columns, and these big massive things were big ducts at the time. And by the time we got to the 1950s, the Seagram building, which became to fame for two reasons that are interconnected. One, rated the most significant building in the millennium by architecture critic Herbert Muschamp, partly because of what it created as a normalized footprint with a normalized HVAC system, which in fact from the 1950s has made every office building in the world kind of look like this one, and for the same reasons rated as the worst performing building in Manhattan by the New York Energy Audit in 2012. This is our buildings, isn't it? And it's interesting that this is buildings outside of Europe. 2.8 meters floor-to-ceiling height for us. We're the occupants. All that mechanical stuff, we deal with all the systems, stay above, and that's what left us to a building environment that kind of looks very consistent and normalized like this. Many of our cities look the same. And we kind of frame our architecture around this idea of separating the mechanical and electrical systems like that. 1960s, an architectural scientist, historian, and by Victor Olge wrote a book of bioclimatic design that started framing the stuff on the right that, again, today I could present as novel, but we know is not novel. He looked at this idea of air conditioning becoming this sort of catch-all for all types of questions. No longer do you need to actually build a building anywhere in the world to address its local climate. Air conditioning and mechanical ventilation can address the needs. Building design could be decoupled from climate. Do whatever you'd like. And Victor Olge challenged that, and many folks in the green building and high-performance building design sector always talk about that. Shading is appropriate in some climates, thermal mass in others, and we should look at climate-specific design. I view a lot of this as really questions of culture and not of science. The culture of building design in North America is very different than Europe, in part through the history of how we've separated architecture and engineering. Mechanical systems that seem to be the problem and the solution for everything, and then everything else on the side. The culture is kind of what leads to some of these paradoxes. This was a school here in the Lower Mainland that in the midst of the pandemic, the teachers in a wing of the school that had no mechanical ventilation went to open the windows, and officials in the school came and shut them and locked them closed due to security constraints. There was no guidance that said open the windows. There was nothing that went into the detail saying it was imperative within the guidance, at least within the facilities management guidance, to keep the windows open as much as possible. Even bring it home to high-performance buildings. This is the first project I initiated at UBC, wrote a proposal for a 6-story passive house building that's just about completing construction, and it's located on UBC campus. It's going to be for staff and faculty in the university. It has a lot of amazing traits for a high-performance building on the West Coast, somewhat European-like. It has tilt-turn windows that can be open in different positions and fully open. It also has exterior movable blinds to provide exterior shade, which is quite rare, so rare that the contractors had to make these movable blinds on site from scratch. They were installed. Designers, everyone behind the project on board. Then the properties managers of the same developer came in and said, well, wait a second, Vancouver, you can't open a window more than 5 degrees. You can't. You're not allowed. You need to install arresters. There was a lot of pushback, and the arresters won. That window on the right is open as far as it can go. You can't reach your hand out to actually move the blind. That costed a heck of a lot of money to put in the building. What might now happen is there's going to be a YouTube video released to the tenants as they move into the building to give them instructions on how to remove the arresters so they can open the windows fully. That is where a culture of not even thinking about the outdoor environment and our connection to nature as occupants and building designers takes us. Why? Well, because a building has a mechanical system that will be able to keep people cool and hot. What's the need for windows? It takes us to Munger Hall, if anybody remembers this story in the news. Warren Buffett's investor buddy, who's like 90 plus, designs a building saying this is the way you're going to get thousands of students into a residence and make it affordable. How do you do that? Oh, if you missed, I don't know if I can go back. Oh, perfect. You have a large square dorm where the majority of residential suites inside this dorm have no windows whatsoever, no view to the outside. Imagine an 18-year-old living as an adult for the first time, seeing this is the society that I'm growing up into. This is the value system that's being placed on me as a resident and as a person that's trying to live in an environment around us. It's why this connects to cooling. The International Energy Agency projects that the global south, largely, as well as a few regions like ours in the world, will see an increase of cooling demand over the next decades of about 300%. And if the adoption of air conditioning, mechanical ventilation air conditioning with a COP of 2, et cetera, proliferates, that will likely short circuit and diminish much of the savings we're going to get from energy efficiency and heating reduction in the world. If 300% increase in demand and cooling arises, that will only make our situation with regards to climate mitigation and climate change worse. On May 17th, one of the last wealthy regions of the world yet to adopt building cooling implemented a new bylaw that will require every new building to have a mechanical cooling, and within the requirements I would interpret that to mean a mechanical ventilation-based cooling system by 2025, and that's here in Vancouver. The last wealthy region of the world that has some capacity, some resources to innovate and make a demonstration of a different path forward before we have 1.5 billion people saying, well, if they did it that way, what are we supposed to do? It goes back to Lytton, and it goes back in partly to this. Through COVID guidances in North America that minimize the value of opening windows, and in fact are in some residences recommending you don't even need to open a window, requirements on conditioning that are not saying balance measures of design with some cooling measures, in fact giving no other measures except for saying air conditioning. Ostensibly, we can have developers here interpreting this to say you don't need openable windows in buildings. In fact, the openable nature is like a window dressing thing. People like the feeling, but it doesn't actually have to work. I wonder if in 20 years from now, we're going to see this in a different light, the way we looked at history with the OPEC crisis and sick building syndrome. In 1970s, ASHRAE and through many well-intentioned measures implemented a new energy efficiency code due to worldwide gas shortages to try to minimize energy use for heating, cooling, ventilation. The science of the day would say we could reduce ventilation without much of a risk, and so they did so, drastically reducing ventilation in buildings that 20 years later we came to realize was actually causing people some illnesses and some headaches and a wide range of other symptoms, some even more severe, until we alleviated that by increasing ventilation rates. And I wonder to what extent we might have in the last few years, through all the need and the urgency to address COVID and viral mitigation in a building as well as climate, implement and recommend measures that might have very short-term gains but potential long-term consequences that we've in fact experienced in the past. Prior to the pandemic, we would show graphs like this as educators, and in fact as practitioners, saying the 20th century was a very mechanical century for how a building would operate. And in the 21st century, if we take seriously our climate mitigation targets, we need buildings that are far more integrated with nature and natural systems, not buildings that are totally passive, but buildings that have some capacity to deal with extreme shocks, but are still far more livable buildings than we had in the 20th century. And right now, in the last few years, in fact, our guidance have been taking us back right into the 1950s and 70s. And I'll leave you, in fact, with a building like this. I tell my students, in fact, last year we had this building a lot propped up in the department. This is my favorite building in the world. I think it is, but I'll just say it. This is my favorite building in the world. This is Baumschlager Eberle. It's an Austrian architecture firm, and this is House 2226. 2226 stands for the temperature band that this building is designed to provide inside. This building has no mechanical ventilation, heating, or cooling system whatsoever. It relies solely on natural ventilation and internal heat gains. The entire thermal mass, the size of the rooms, the way heat from the occupants are released in smaller contained spaces, and the quantification of that from the German articles written about it would translate that to say that humans are the heating machines. And 4 people in heat in the wintertime would generate 75 watts sensible times 4, so you got to size your R value in your wall according to that. And in the summertime, natural ventilation and thermal mass and night flush cooling and a lot of interventions that matter allow this building to operate within this band. In a 49-degree day, could that be resilient? Probably not. But at least incentivizing a building that operates like this the other 85% of the year would be way better than what we might be giving today as guidances. And it's a great building. Look, I like the minimalism. It's kind of speaking to me deeply. And there's data that reports on the building. It's not really a sort of a fiction. This building has, for the most part, operated within its thermal regime. Ventilation may be a little bit wonky in terms of having higher CO2 than we might see in a mechanically ventilated space, but certainly operating and making a great point that you can have buildings in the 21st century that don't even have an HVAC system and you're complying with code. So what are we talking about when we rely too heavily on mechanical ventilation and not a balance of measures? And so then, my conclusions. Absolutely under extreme heat, a ceiling fan, exterior blinds, they're not going to cut it. These measures that sort of are passive in nature, that are good for us in terms of feeling, obviously in extreme heat, they don't cut it. Definitely filters, filtration, UVGI, and a lot of technology that is important when there's smoke outside or where there's a virus, those are also likely to be important in a crisis and shocks. Yet, none of these truths should govern how we design healthy, climate-resilient buildings that are well ventilated and comfort. And so, in fact, my 2 biggest recommendations for those of you who might have connections with the policy discourse on this or want to continue the discussion, I think we absolutely have to stop using the term air conditioning and mechanical ventilation when we talk about fresh air and cooling. They are not the same. Cooling may be synonymous with air conditioning, but air conditioning is not the only way to deliver cooling. Mechanical ventilation can give fresh air, but there are other ways we can provide fresh air into buildings that are actually healthier for us, because we know them as humans as we occupy buildings, that we want these other features to make us feel more comfortable. And so maybe, and this is the one that's the most controversial, for those who are ASHRAE members, I was a member of ASHRAE, but that is not a point. I'm going to be deliberately controversial on the last point. This is not to make a point that if you have your building codes and standards written by an organization that's led by the air conditioning industry, that there's some sort of nefarious connection there. It just means more that you might not have a balance of all of the different expertise that's required to really articulate the question of a healthy building. And in fact, if we cannot resolve that through ASHRAE codes, maybe we need a different set of codes that address that. I know of a consultant in Vancouver, and I spent time in the UK that at least know the standards, that has started deliberately applying CIPSE codes to building design here. Not necessarily circumventing ASHRAE, but saying we're compliant with ASHRAE if we do that, but that code gives us a credible path to a different approach to having a building that balances hybrid design measures with mechanical systems, and that doesn't rely so solely on a mechanical ventilation answer to all of our ills. I kind of like that because I don't want to be a bubble boy. I don't think any of us want to be bubble people necessarily in the built environment, but we do have a problem now if we see the way the guidances in the last few years are taking us. Thanks very much.
Do we have any questions? Or Matthew, anything online? Yeah, sure, come on up. Got time for a couple, so if there's another one, feel free to join the line.
That was a great presentation. Thank you very much. Just wondering if you could talk a bit more about radiant cooling.
I would love to. I mean, we have an office space, and in fact, the one that I was talking about would like to outfit that with radiant cooling panels. It is an interesting technology to mention that. I wonder how many in the audience have heard of it before, and yet if we were having a similar discussion within the trade in Central Europe, it would be, radiant cooling panels. I mean, these are panels, you put cold water, hot water in them, and the body, interacts with that panel via radiation, and that's common in Germany and others. And it's not common elsewhere because some of the first generations of these panels, the idea of surrounding the human body with cooler surfaces, they failed or weren't functioning well, especially the cooling panels, condensation. If you have cold water exposed to a hot indoor environment, you can have condensation. That's going to have that system fail. What we see now with some of the emergent materials and technologies is that you can have radiant cooling systems. You can expose the human body to a radiant temperature that's much lower than the ambient because it's occurring in the infrared spectrum where we can deal with materials differently than the visible spectrum. So a plastic bag is transparent to infrared. The surface temperature of the polyethylene we surround the radiant panel with is above ambient temperature, or it's close to ambient temperature, above the dew point temperature. So if ambient's 25, we have the plastic bag at like 24. But because it's transparent to infrared, the human body is seeing what's behind the plastic bag, which is a cold surface that's kept at 15 degrees Celsius, which would otherwise condense in the indoor environment. But because it's actually isolated from the air environment with that plastic bag, my body can interact with it even though the air doesn't. And with radiation, that's all it is. It's a different way in which heat transfers that has nothing to do with the air temperature. It has to do with the geometry and the positioning of the human body and the surfaces around us. If we surround the human body with cooler surfaces, we can achieve a similar heat flux as we would if we have a cooler air temperature around our body. The benefit, though, is it takes a lot less energy to cool surfaces than it does to cool the air. And we require much warmer water in the cooling season to do that than we would in an air conditioning setting. And I could talk more about it, but I probably will then talk too long about it.
I think, is there an online question? Yeah.
So we have an online question here. They ask, are there any passive cooling or ventilation systems that can also reduce exposure to wildfire smoke, i.e. filter the air?
I'm not, I would say, I don't want to say yes or no. I would say generally it is, of course, an aspect of, passive performance is very difficult to do. We're talking about fine particles that have a certain amount of driving force that you need either with wind or other measures to kind of get it through a filter. And so, long story short is I don't know of any that are sort of commercially viable, off-the-shelf kind of design measures that work very easy. I do know of similar types of technologies in the pipeline like porous walls that provide filtration with wind driving forces, so you could at least have the windows closed and air leaking through a wall. But that is, I think, much more in the research territory than I've seen anything. I would, one would have to capitulate that under those extreme risks, that's where we may need to have, and we should have, mechanical systems. But hopefully, that is not our entire year of our ecosystem.
So my image, when you were asking that question earlier, was outside of a cob house. So my question has to do with the feasibility of balancing, because most of the time when you're talking about thermal mass, you're talking about concrete. So balancing the carbon intensity of concrete with potentially alternative materials for thermal mass. So my question specifically would be the feasibility of alternatives to concrete for thermal mass.
So I think as a perfect example, we have students at UBC right now that are doing the first solar decathlon home. Solar decathlon is a U.S. competition where students build a single-family home. And this will be a single-family home and a living lab for kind of applied climate chamber studies. And the goal of the project is to make a zero embodied carbon structure that doesn't have a mechanical cooling system and is relatively comfortable. And the answer to that is hempcrete. If you haven't heard about hempcrete, hemp, which is fibrous growing material plus lime binder, generates an aggregate that has thermal mass and is carbon negative. It actually sucks more carbon from the air than it produces. So this will be a structure that has massive hempcrete walls as a form of thermal mass and no concrete. And we'll discover whether it works. And science point to, at least the studies that we know of, point to it being an appropriate alternative. I think there are likely to be more emerging alternatives to concrete, particularly for thermal mass of that type.
Okay.
Thanks very much.
One more time. Thanks, Adam. Here you go. Don't leave yet.